Stanford University.
We're actually moving along rather nicely, I think. We are getting to the point where we have covered the absolute minimum of what you need to know to go on. But still, we're going to learn some more about classical mechanics, and probably a good deal more. All right, if there's no other questions, well, we still have a minute or two, so I won't start for another minute with a formal lecture. Yes, sir?
That you would recommend?
Yeah, I think there's a pretty good textbook by Griffiths, isn't there, on classical mechanics? Griffiths, David Griffiths. Yeah, there's the classic book that I learned out of 50 years ago or more. Yeah, more than 50 years ago. Herbert Goldstein, Classical Mechanics. He's not even a physicist. He was an engineer, I think a chemical engineer or something, and decided to write a book about classical mechanics, and it's been the gold standard ever since. Goldstein.
You know Lanchos, the variational mechanics or whatever it is?
Yeah, there's a book by Lanchos on variational principles, I think. How do you say it? Lanchos? I don't know. Yeah. Well, look, this is a good, all right, look, we have this group that sort of acts as a, not as a blog, what would you call it, just a group. Somebody, whoever wants, put out some suggestions for some books. My problem is I don't read. I don't know how to read. So I don't read very much. I can write beautifully, but I can't read. No, it's not true. I read a lot. But I'm always the wrong person to ask for literature surveys. I almost never know. That's why it's easier for me to write a textbook than it is for me to go to the library and find one. That's why I do it. Okay. Shall we begin, or does somebody else have a physics question? Politics question? I don't know anything. No politics. What's that?
Is the neutrino issue resolved?
No, it's not resolved. I think people are starting to get some idea that it has, they don't see a neutrino go past them over here, and then over here see a neutrino go past them. There's an accelerated beam. The accelerated beam is a pulsed beam. Protons come, and the pulse has a certain shape. The pulse shape is, or the width of the pulse of protons coming is much broader in time than the discrepancy. Yeah, so they really have to study the shape of these things and so forth. And there's some questions about whether they, I certainly wouldn't say whether they know what they're doing. I don't think that's the issue. But, whether they know what they're doing when it comes to the exact shape of the pulse and when the, no, it's not the shape of the pulse. The pulse they know. But I think one of the questions that I understand is the pulse comes, it heats the target gets hot, the next piece of the pulse comes and it hits a hot target. The hot target, I guess, is full of things with velocity. I'm not sure if the point is that the velocity of the target gets imprinted on the pulse and distorts the pulse. Anyway, I don't know. What's that? No. Wait. Yeah. Okay, so I heard from my student about this. He didn't know what it was about, so we sat down and did a little calculation. It's not a question of special relativity. Are you interested in what this Dutchman said? I mean, it's almost certainly not the solution of the problem. I don't think these people made a really dumb GPS. They have real experts. Okay, so here's what the Dutchman said. Dutchman is not being used in a derogatory sense. It wasn't. The Hollander. And he's a smart guy. I mean, it was a smart point. But he said there's a satellite. The satellite beams signals back and forth. Over here we have the source. which is called CERN. Over here we have the target, which is called the Grand Sasso Mine. And in fact, this is only about 500 miles. On the other hand, the satellite is way up there someplace, but nevertheless, I'm going to draw it over here. And he said, well, if you're in the rest frame of the satellite's moving. The satellite's moving with a pretty significant velocity. It's about 22,000 kilometers high. It's moving with whatever velocity is appropriate for it up at that height. It's not in geosynchronous orbit, so it is moving relative to the Earth. And what he said was, well, this is the picture you draw if you think the satellite was standing still. And there's the target. A light pulse goes from here to here. He says, during the time that the light pulse moves, the target moves to about over here. Incidentally, I don't know exactly what he said. I did read the paper, but his formulas were the same as mine, so I think he must have been saying the same thing. And he said, during that period, so really, the target was over here, not over here. And so the time delay for the signal to get from here to here is really a little bit shorter by an easily computable amount. And the amount is about 15 nanoseconds. He, I think, correctly points out that there's another effect from this end over here. Signal goes out from here. It's not really a signal going this way and this way, but I think you can think of it as a signal going from here to here. And he said, well, for the signal to have gotten to here, it had to have started a little bit earlier. So you get two effects in the time of flight of the signal from source to target. Each discrepancy or each difference was about 15 nanoseconds. I worked that out. That's right. And therefore, altogether, you get 30 nanoseconds. And then he said, well, just maybe they did this twice. They made the error twice. I do not understand why he thinks they made the error twice. I don't know. And so it could all add up to 60 nanoseconds, which is the right discrepancy. I would be stunned if they made this mistake. But they didn't make that mistake.
It's being accounted in the receiver on the ground.
What's that?
Is the fact being accounted in the GPS receiver?
I'm sure that's accounted for. I mean, exactly.
Otherwise, the error, position error would be already 5 meters just from those.
Would you call this relativistic, this effect?
Look, I don't believe this. I wanted to see whether the order of magnitude of the effect was about that. And it is, but there's no chance that they make this error.
Would you call that relativistic data?
No.
Because in his formula, he has the Fitzgerald, whatever, contraction.
There's a tiny Lorentz contraction, which is much smaller between these, which you don't have to add in. It's completely negligible. I think it's about 10% of the, so no, I don't think so. But, it does involve light, it does involve motion, it does involve relative motion, so you can call it what you want, but they didn't make this error. I think. Anyway. I don't think there's much point in talking about it. I think it's going to wind up being some highly technical, difficult issue involving the beam pulse and things which are way beyond my knowledge of that kind of thing. So I think you just sit and wait. Okay, I want to go back a little bit to what is really at least half of the heart of the subject, namely the subject of symmetries and conservation laws, and just really quickly go through it. I was a little bit dissatisfied with my own discussion of it last time. I think I probably didn't make sufficiently clear what a symmetry is and the difference in particular between active and passive transformations. You can think either way, active or passive, either way, there's an appropriate argument that gives the same result. But let me just spell it out for you. Let's think about it the following way. We have a particle on a line as an example, just as an example. And now somebody comes along and says, perform, that's something you're required to do. Perform the transformation x goes to x plus 1. What exactly does that mean? Oh, incidentally, we imagine that the line is coordinatized so that every point on it is labeled. Every point has a name. This one is named x equals, well, this one's called named x equals minus 1. This one's named x equals 0, and so forth. Think of the coordinate labels as just the names of the points, if you like. All right, but of course it's done in a special way, not arbitrary. What does it mean to say perform the transformation x goes to x plus 1? It could mean two things. It could mean relabel the points so that every point that was originally labeled x is now labeled x plus 1. This one was originally labeled x equals 0. And after the relabeling, it becomes, let's call it x prime equals 1. Particle stays in exactly the same position. If it happened that there was a potential energy, for example, that looked like this, the potential energy would not change because the particle hasn't moved. Right? Okay. The other definition of what you could mean by perform this transformation is take the particle from where it is, keep the coordinates fixed, but move it. Wherever it is, whatever x it's at, move it to x plus 1. Under that transformation, the potential energy does change. The first notion is called a passive transformation. You don't move anything, you just relabel points. The second version is called an active transformation. You literally take everything in the system, not just one particle, but every particle and whatever else you have besides particles, and lift them and move them 1 unit to the right. That's an active transformation. It's quite clear that the active transformation, since it moves the particle, will change the potential energy. Yeah?
So then whatever is causing this potential energy to exist is not considered part of the system?
Right, exactly. Exactly, and we're going to come back to that. That's exactly right, so let me state it now. In saying that the system was a particle, we of course are first of all making an approximation, but more than that, we're dividing the entire system into two parts. One part is the particle, the other part is the Earth with all its hills and valleys and so forth. Okay. If I, of course, were to move everything, including the Earth, the potential energy would not change. Okay? But what we're focusing on is the particle thinking of the Earth as just too heavy to respond. It's a situation where, with essentially no loss of accuracy, we can say the Earth just doesn't move. Of course, there's a slight loss of accuracy there. If the particle accelerates or decelerates, it recoils against the Earth moves a little bit. But because the Earth is so heavy, it's irrelevant, or it's for practical purposes. We can ignore the motion of the Earth, and we just say the Earth is fixed. It gives rise to a potential which is a definite function of x, and we're going to leave it that way. We're not going to change the location of the Earth. We're not going to change the location of the top of the potential, for example. And we're just going to say the transformation we're going to do is to move everything relative to the Earth, in effect. Okay? So, but we simplify it by just saying there's a potential energy which is a function of x, and therefore, if we move the particle, the potential energy changes. Okay, so that's the notion of an active transformation. And I think it's easiest to think about, the active version.
So one thing that still confuses me, even with this description,
Yeah.
when we did the rotation last
Yeah.
time, so we not only changed the positions, we changed the velocities.
If you change, no, we didn't change the velocities. Well, yes, okay, yes, we did. We did. We rotated the velocities. We rotated the velocities. Okay? Right. So the velocity was a vector, and when we rotated all the positions, we also rotated the velocity. Okay? We not only rotated the position at an instant of time. I should say, okay, one more thing. When we say do the transformation x goes to x plus 1, we mean at every time, all times, send x to x plus 1. When we say to rotate the coordinate system so that x varies a little bit, we mean at all times. We'll come to it in a minute. We're going to talk. I'm going to go back through it just to refresh you very quickly. All right. So here's the game. We have some configuration space, which is the space of the q's. The q's. Incidentally, I will use x when thinking about Cartesian coordinates for particles. Otherwise, more generally, we'll discuss q's, but x's are just a special case. All right, so we have our Q space. Here's our Q space. The system, and it's multidimensional, or it's not multidimensional. It's got some number of dimensions. And a configuration is just a point in that space. Now, there are many configurations. All right, for every point in the space, there's a configuration. And now, what we mean by a coordinate transformation, an active coordinate transformation now, is that we take the system, wherever it happens to be, and move it to a new position. We move it to a new position. If this point is called q sub I, then we shift q sub I by an amount, let's call it delta q sub I. It's a shift of q sub I by amount delta q sub I. This is delta q, right, which may, in fact, depend on where we are. In other words, the delta q over here might be different than the delta q over here, might be different than the delta q over here, but it's fixed. It's fixed once and for all, meaning to say that there's a definite transformation, but the transformation, the amount that you shift, may depend on where you are. That's allowed. Okay, so then delta q sub I is not just a constant then. It depends on where you are, and in order to indicate that, we introduce a function for each I, which is a function of all the coordinates, and a small constant delta. Now, the small constant delta is just really for bookkeeping. It's kind of a redundant notation. If we just thought that f, we could imagine that f was just small. But it's a sort of redundant notation. We'll think of f as not necessarily being small, but make the shift small by having a sort of universal constant, which is assumed to be small, so that delta squared can be ignored and so forth. All right, this is the nature of an infinitesimal coordinate transformation. Every point moves, and the coordinates of the points may move by an amount which depends on where you are. That's this over here. All right, that's an infinitesimal coordinate transformation, and that's what we mean when we speak of of an infinitesimal coordinate transformation. Now, when you do so, the potential energy may change. Of course, the potential energy may change. This is an active transformation. It may even be that the kinetic energy transforms. Okay, let's say what happens to velocities. Oh, the one thing that we do assume is that these f sub i's are independent of time. When we shift things, we shift them by amounts which don't depend on time. Okay. For example, if we're just talking about a shift of x goes to x plus a small amount, that small amount is assumed not to depend on time, and therefore, in that case, the velocity itself does not shift. The velocity doesn't shift. If we made the transformation x goes to x plus a constant, then if we time differentiate this, it says that x dot goes to x dot with no change in the velocity. Okay. Why? Because we moved everything to the right by 1 unit, moved it both at time t and also at time t plus a little t, plus a bit, and so the velocity hasn't changed in between. Okay, so in general, there may be a change in the velocity, but for this particular case, there would be no change in the velocity. Yeah?
Is that
final delta there in your equation, a constant across all points?
This delta is a constant, yeah. This delta is a fixed constant, which in the end of the day, we'll say is very small. Okay. And it's just a bookkeeping device so that we don't have to call this small, that's all. We'll see why in a moment we don't want to call that small. It's a bookkeeping device to say all the transformations are small and of the same order of magnitude. Good. Some of these f's may be 0. For example, if we're talking about two-dimensional space, x and y, we make a transformation only of the x-coordinate. X goes to x plus a little bit with no change in y. Then the y component of f would be 0, the x component would not be. Okay, so as I said, we keep track of the smallness by the constant delta. All right, as I said, when you do such a transformation, the potential energy will in general change. Okay. It may not, but it may. It may change. In addition, even the kinetic energy may change. For example, the kinetic energy in some coordinates, in some non-Cartesian coordinates, might have the form, it might have the form of T of Q. That's just a function, any function of Q times Q dot squared. Some function. An example would be polar coordinates in which the theta term, the term associated with the theta velocity, involves r. Remember that? R theta dot squared? Right. So you can have kinetic energies which also have dependence on Q. And then when you move things, even the kinetic energy might vary if you make a transformation. So in general, the entire Lagrangian may vary when you, and usually will. The situation where the Lagrangian doesn't change, and moreover, doesn't change no matter where you are, not only at the point where the system happens to be. You might say, all right, I'm interested in the system being right over here, and then I do a transformation which takes it over here, and find out that it doesn't change the Lagrangian at this point. No, that's not enough to say there's a symmetry. To say there's a symmetry means that at every point, no matter where you are, the Lagrangian doesn't change. Okay? For example, for potential energy, let's just think about what it would say about potential energy. The potential energy is a function of x and y. And the coordinate transformation I may be interested in is just an x shift. Let's take the case of just an x shift so that x shifts a little bit. What does it mean to say that the potential energy doesn't change if you make an x shift? It means it doesn't depend on x. No matter where you are, up or down, left or right, if the potential energy doesn't change when you vary x, what does it mean about v? It means it's independent of x, but it can depend on y. It can depend on y because y doesn't change when you shift x. On the other hand, if I were to say a different type of transformation, shifting vertically and saying the potential energy doesn't change, would say v was a function of x. And if you were to say even stronger that the potential doesn't change no matter which direction you translate in, it would say the potential were a constant. The potential was a constant, completely independent of x and y. Okay, so that's the notion of the potential energy changing or not changing when you make a small transformation. But in particular, we mean when we say that the potential doesn't change under a small transformation. It doesn't change wherever you are under that transformation. If both the potential and the kinetic, or let's say it more generally, if the Lagrangian itself does not change when you make a transformation, then that is a symmetry. Okay? Wherever you are, you make such a little motion at all times, then the Lagrangian, if the Lagrangian doesn't change, then it's a symmetry. Yeah?
So the Lagrangian has to stay the same, but does that...
Same value, same numerical value no matter where you start.
But does that condition have to be true separately for the potential energy and for the kinetic energy?
No. In many cases, the Lagrangian doesn't even divide up into a kinetic and a potential energy neatly. So that's a good question, and the answer is no. It does not have to be separate. It's kind of hard. It would be kind of hard if one term didn't depend on velocity and the other did and didn't. But in general, the most general Lagrangians won't divide up in a neat way into kinetic and potential. They'll just be functions of q and q dot. And then it wouldn't even be possible to even ask the question in that case. So the answer is no. Only the whole Lagrangian has to not change. Yeah?
I'm probably reading in too much, but are you saying that it won't change, or that it will change so little we can ignore the change?
Okay. This is an infinitesimal transformation. The most we could expect, if we made such a transformation, would be an infinitesimal change. If we make an infinitesimal shift, the most we can expect is an infinitesimal change in the Lagrangian. To say that there is no change means no first order change, no change proportional to delta itself. Now, that's enough to prove that a finite version of the transformation, which just means doing it repeatedly enough times, usually means a number of times proportional to 1 over the small number, doing the transformation over and over till you build up a finite transformation, that also doesn't change the Lagrangian. If it's the case that it doesn't change the Lagrangian no matter where you are. A simple example would be a potential which you might think depends on x. Okay, you might think it depends on x. And then you say, all right, what happens if I move x a little bit? Then there's a variation of x, a little bit, the variation of the potential, the small change in the potential is just the derivative of v with respect to x times delta x. Now, supposing it's true that this is equal to 0 no matter where you start. And delta x is just a number. Delta x is just delta, the number, the small number. Suppose it's true that no matter where you are, the small shift doesn't change v. Then that says dv dx is equal to 0. And not only does it say dv dx is equal to 0 at the point where the particle is, it's 0 no matter where the particle could be. If this is equal to 0 for all x, then dv dx is equal to 0. And that, of course, does say that v is constant, and it also means that if you were to build up a finite shift by little infinitesimal ones, it still wouldn't change v. So typically, if you have a situation where the small change in coordinates does not lead to a comparable change, in other words, a first order change in the Lagrangian, then that's a symmetry, and you only have to check that the Lagrangian hasn't changed to lowest order, meaning to order delta. Delta squared, you don't worry about. You don't have to worry about it, because as long as it's flat for all x, or more generally, as long as it's, so to speak, flat for all q, then repeating the transformation endless numbers of times won't change the value of the function. Okay, so that's the notion of a symmetry. And when you have a symmetry, you have a conserved quantity. So I won't go through the derivation again. We'll just write down what it is. If this is your little shift, then the conserved quantity, which I called q last time, q for quantity, q is, notice that each coordinate is being shifted. Some of them may not be shifted, but that just means some of these are 0. So the general situation is every one of the coordinates gets shifted. Then q is a sum over all the coordinates of a contribution from each one of the coordinates. And the sum is multiply the momentum conjugate to q sub I by the little shift f sub I. Now you can see why one doesn't want to think of f sub I as an infinitely small quantity. I want to think of this as a, as a finite quantity. So I don't want to necessarily restrict f to be small. Then it follows that the time derivative of this is equal to 0. That's the theorem we proved last time. And you can go back over the derivation of it, but this is kind of the bottom line. We also looked at some examples. Let's go. Let's just remind ourselves of the example. There was translation symmetry. In translation symmetry, let's go back to x. Yeah, x, y, z. An example would be delta x is equal to 1 times delta. In other words, f is just 1. If f is just 1 for x, then it follows that q is just the momentum of that particle. On the other hand, we can generalize this in two different ways, at least two different ways. The first way we can generalize it is to notice that we could imagine symmetries if we had full translation invariance, real translation invariance, that it doesn't matter where you place the system. Then we'll also have the other coordinates and so forth. All of the coordinates will have shift symmetries. And under that circumstance, all the components of the momentum, px, py, and pz, are all conserved. All right, so momentum conservation follows from shift symmetry, from the idea that if you move a system and there's nothing to move it relative to, nothing that influences it, then momentum is conserved. Another direction that we can generalize it is that we can imagine there are many particles. Many particles, x sub I, y sub I, and z sub I. Now, I doesn't label the coordinates, it labels the particles. There are 3 coordinates for each particle. All right? Then what we would want to do, and you can assume the particles are interacting with each other, but as long as the forces only depend on the relative positions, in other words, as long as the potential energy between pairs of particles doesn't change when we move them both, then there's a symmetry not with respect to moving one particle at a time, but with respect to moving all of them simultaneously. In that case, all of the coordinates, let's say the x components, let's look at x momentum conservation. Then we don't just move one particle, we move them all, and in that case, it's the sum of the p sub i's which are conserved. In other words, we have to sum over all the degrees of freedom which we shifted. Okay. So translation invariance means momentum conservation. Again, I'll just emphasize, it doesn't mean we're not talking about motion of one system relative to another if they exert forces on each other. We're talking about the entire system being displaced. If the Lagrangian doesn't change, we have a symmetry. The circumstances under which that wouldn't be true is if we had some object which was very, very heavy, so heavy that it doesn't move. We don't think of it as part of the system. There it is. But we study the motion of the system relative to that object, then we won't have a symmetry. Then the potential energy will change. Okay, that's, let's just remind ourselves about rotation. Rotation was a little less trivial example. Let's talk about rotation of the xy plane. If this is x and y, and let's for the moment suppose we have a single particle, then if we make an infinitesimally small rotation, that means we rotate the position of the particle by an infinitesimally small angle delta. Well, it's not very well drawn, but I think you get the idea. We shift everything, no matter where the particle is, we shift by amount delta. Then the coordinate transformation is delta x, the small change in x when we rotate. Now think of this as a rigid rotation of the plane. The small change in x is y times delta. No, minus y times delta. if we're over here in this sector, yeah, minus y times delta. And what is delta y? That's x times delta. All right, you can work that out. OK, let me show you how another way you could think about this fact here. If it's true that this represents a rigid rotation, then it must be true that it doesn't change the length of the vector xy, the length or the distance from the origin. Here's our point. Wherever it is, we rotate a little bit by angle delta, and the particle moves to that point. Let's ask, does this transformation, this infinitesimal transformation, does it change the distance from the origin? Better yet, does it change the square of the distance to the origin? So let's write down the square of the distance to the origin. R squared is equal to x squared plus y squared. And now let's say, supposing we make a little shift, what happens to r? Okay? So in particular, we can calculate the change in r squared. The change in r squared is equal to twice x delta x plus twice y delta y. If you have a product of two things and you make a variation, then it becomes delta A times B plus A times delta B. All right, so applied to x squared plus y squared, the change in r squared is 2x delta x plus 2y delta y. Now let's plug in. Delta x is minus y times delta. Delta y is plus x times delta. These are going to cancel. This one is going to have a 2x y times delta, and this one's going to, one of them is minus. This one's minus, and this one's plus. And they're equal and opposite. All right, so that's one way to check that this is, in fact, a infinitesimal rotation, that it preserves the length of all distances from the origin. You can do better. You can prove that this is the form of a rotation. OK, now that we know that, we can feed it into this formula. It's a mechanical process now of feeding into this formula and constructing the conserved quantity, assuming that the Lagrangian doesn't change. The circumstances under which the Lagrangian doesn't change would be, for example, that the potential energy is only a function of radial distance. That would do it. Oh, incidentally, when you do this, you'll also discover, just by differentiating the formula with respect to time, that the change in the velocity, the x component of the velocity, is minus the y component of the velocity times delta, and the change in the y component of velocity is equal to the original x component of the velocity times delta. And you can feed that into x dot squared plus y dot squared and see that the kinetic energy doesn't change. Kinetic energy doesn't change. Distance from the origin doesn't change. So if the potential energy only depends on the distance to the origin, the Lagrangian doesn't change. We have a symmetry. The Q that goes with it is, all right, there are two terms. There's p sub x times the little shift of x, that's minus y, minus y px, and then plus xpy. Now, this, I think most of you will notice, is, first of all, it's called the angular momentum. It is the angular momentum. It is also a component of the cross product. If we call this, if we think in 3 dimensions now, we imagine that we're in 3 dimensions, put back the z-axis. Doesn't change anything that we did. We're still rotating in xy. This is the vector r, or let's call it little r, the vector r that represents the position relative to the origin. Then this is nothing but the z component. This is the z component of r cross p, cross product. Not x, but r cross p, cross product, r cross p. It's the z component of that, z component of it. So it says that the z component of r cross p, which is the z component of angular momentum, is conserved. All right, that's what angular momentum is, r cross p. Now, if this is true, let's think ahead a little bit. If we're really thinking about a three-dimensional problem, we got this conservation law by considering rotation of the xy axes. Right? Focus the z, looking down the z-axis and rotating. We could do exactly the same thing looking down the x-axis and rotating the yz plane. Right? If we did so, we would find all of the components of r cross p were conserved. And in fact, well, okay, this is the first one. This is the z component. The next one would be y minus z py plus y pz. And what's the last one? Y zx pz plus z px. These are the three components of the angular momentum. The angular momentum is a vector, and these are the three components of the angular momentum for a particle, and they're conserved if the potential only depends on radial distance in the three-dimensional sense. If the potential depends on radial distance. Now we can generalize this in yet another way. If there are many particles, and even if they're interacting with each other, as long as the potential energy, the sum total of all potential energies, but in particular the individual potential energies, as long as they don't change when you rotate, again, we rotate everything simultaneously, then the conservation law just becomes the sum of all the particles of r cross p. And that's angular momentum conservation. But the importance for us is that it follows from symmetries, assuming that the system is symmetric. Okay? So, for example, a planet in orbit around a star, if the potential energy only depends on distance, therefore it's invariant under every possible rotation you can do that holds the star fixed, okay, all components of angular momentum are conserved. Questions? Yes?
Yeah, if you imagine like a two-dimensional, like a cone that comes
Like
from
a
an
what?
exact point, and x is exactly at that point. And if you add a delta, I mean, or just one dimension, there's a v, and it's right at the point. If you do a delta on the one side or the other, you have much different Lagrangians. You know what I'm saying? It's like an unstable point, and the delta has a significance as to which direction it is.
Yeah.
What is that? How does that relate to all of this?
Well, for our purposes, we're going to assume that all functions have unique derivatives. You do have to worry about things like that. It's a legitimate worry. But for our purposes, I think, and we're going to say, if we have a thing like this, it really means this. And we'll assume that all functions have a unique derivative at every point. Of course, if you really had well, okay, that's something we'll assume. Everything is differentiable, continuous, no funny businesses of different limits coming from different directions. Such things would lead to modifications of what I'm saying. It's true.
Like if I have a penny on the top of a pencil point.
Well, being at the top is not a problem. The derivative is flat. It's a position of unstable equilibrium. It's true. It depends, but it's not a. Okay. Yes.
So you very early on said delta does not depend on t, therefore x dot goes to x dot. There's no transformation change in x dot. But yet in the rotational case there is.
Okay, all you do, right. The rule is that the change in the time derivative of a coordinate is the time derivative of the change in the coordinate. Okay, so that's the general rule. If the change in the coordinate happens to involve the coordinates themselves, then the change, this is what would follow. Right. So this is the rule that you count on. Yes.
So you mentioned in passing before that the Lagrangian might not separate into the potential and kinetic energy.
Right.
Is that because it could take a complicated functional form, or is there some other concept?
It
of
could be for
Lagrangian?
more than one reason. I mean, it could be because you're using funny coordinates. It could be because you're using funny coordinates. The motion, we've talked about this before, the motion of a particle in a magnetic field has three terms, really. X dot square plus y dot squared, typical standard kinetic term, a term which might be a general potential energy, and then there's this velocity-dependent term, which contains both the x's and the velocities. So there's an example where there are terms which contain both the x's and the velocities, and when you shift things, you have to shift things consistently. So a variety of different reasons it might not separate into conventional kinetic plus potential.
But the Lagrangian is still defined as T minus V, is that?
No, in that case, you do not try to represent it in terms of T and V. It is only if the Lagrangian are. When do you say that it's T and V? The general rule is if the Lagrangian has the form of some function, I called it T before, of Q, something quadratic, we can even make this more general, I and J, sum over I and J, Q sub I dot, Q sub J dot. You know what I mean by that? A quadratic form in the velocities. And then minus something which depends only on the Q's. A thing which is quadratic in the velocities is called kinetic energy. A thing which does not contain the velocities altogether is called potential energy. When it divides up like this, then it's simple. The Lagrangian is just T minus V. But there are situations where you can have mixed dependencies. For example, things involving Q dot times functions of X, some functions of Q. These have neither the form of something quadratic in Q, nor are they simply functions of Q. Then you have to simply think of the Lagrangian as a function of Q and Q dot. It's just a function of Q and Q dot. Not profitable to try to break it up into... All right, which raises the question, what do we mean by energy then? Right, we're going to come to that. In fact, we're going to come to it, I think, right now. Yeah.
Question, I think in the first class you talked about a chain just hanging like, and you said the concept of at least action was applicable to the shape of how that, or am I confused?
No, I didn't say the principle of least action. In that case, it's the principle of least energy. Yeah. In that case, you're not talking about the motion of a system. You're talking about the equilibrium configuration.
So is the Lagrangian used?
Well,
In a different form? If not pertinent now, let's just get to the
here's our equations. dP sub I by dt is equal to minus... In the situation where you can divide things into a potential energy and so forth, the V sub I by the Q sub I. Remember that? That's the Euler-Lagrange equations. If you have a situation which for one reason or another you expect to be static, in other words, no motion, then this is zero. In that case, you just say dV dQ is equal to 0. What does that mean? That means you're at the stationary point of a potential. Who asked me? Yeah. Okay? Right. So a special case of the Euler-Lagrange equations is just the equations for equilibrium when you know for some reason, or when you ask that nothing be changing with time. Good. Okay. Let's move on to energy. Let's assume for the moment that the Lagrangian does have the form T minus V. T minus V, as I said, seems a little peculiar while subtracting the two energies. Does seem a little peculiar. The one thing we haven't talked about yet is energy conservation. Is energy conservation associated with a symmetry? That's the question we want to discuss tonight, and that will bring us to the notion of a Hamiltonian. The answer is yes, but it's not a symmetry of the type that we've discussed. It's not a shift of the Q's. Okay, so let me draw a picture. Let's think about space-time. And the horizontal plane here could be space. We're not thinking about relativity, incidentally. We're just drawing a picture of space and time. These two coordinates could be x and y, or we could just call them q1 and q2. These might not be Cartesian coordinates, but there's some general coordinates. And the vertical axis here is time. And now we think about some experiment taking place, some process taking place, which begins at some time. Oh, well, let's go back a minute. So far, we've discussed translation invariance, which means sliding the system by translating it. We've discussed rotational invariance, which means rotating the plane here. Now we're going to discuss another invariance, which is time translation invariance. What it means is you imagine an experiment taking place. Over here is the start of the experiment, and you start the experiment by prescribing some initial conditions. Initial conditions mean the position and velocities of every molecule or every particle. You start with some known initial conditions, and you wait a while, and after a period, there's an outcome. There's the income, and there's the outcome of the experiment. After a certain amount of time, you started at, let's call it T0, and you ended the experiment at T1, and there's a result to the experiment. Okay. Now, supposing we time translate the whole thing. Now I mean an active transformation. Instead of starting the experiment at T0, we started at a later time. But we also ended at a later time. Exactly the same experiment, except displaced in time. How much displaced in time? By an amount that we'll call delta T. We displace the initial part of the experiment and the final part of the final detection, or whatever it is, by the same amount. Everything has just been shifted. We did the same experiment. Instead of starting at noon and ending at 1 o'clock, we started at 12:01 and ended at 1:01. Right? Is the physics, are the results of the experiments the same? Okay, now that's going to depend on whether the system we're talking about is time translation invariant. How could it not be time translation? That's the definition of time translation. Every experiment is insensitive to such a shift of delta T. Can you think of a situation where it might be sensitive to it? It's a condition of yeah. So for example, here would be an example. You have a capacitor. You don't have to know anything about electricity and magnetism now. A capacitor is just two metallic plates, some plus charges on one side, some minus charges on the other side, and you put a charged particle in here. The charged particle will accelerate. There will be a Lagrangian. There'll be a potential energy of the particle in here, and the potential energy, in fact, will be proportional to the distance along here. And if the charges on the plates were constant in time, then we could shift the experiment forward, backward in time. It wouldn't make any difference. On the other hand, we can imagine that these plates are connected to a battery or a generator and being charged up. start with no charge on them and slowly ramp up the charge in a way that we have complete control over. Assume we have complete control over it, so we don't have to think of the capacitor as part of the system. Because we have such good control, we just say we know what the capacitor does. What about the particle motion? Thinking of the particle as a system. Now, the result of an experiment will depend on when you begin. By the experiment, I mean now, not the process of charging up the capacitors. That's given. That's frozen. It's being done by somebody else out of the room. You're doing the experiment inside the capacitor plates. It does depend on when you start. You'll get a different answer if you start when it's charged or when it's uncharged. So that's an example where a system would not be time translation invariant. Of course, you might argue, and you'd be right, that if we did the whole experiment, including whoever it is that is charging up the capacitor, did the entire experiment, and shifted everything forward by some time, then we would get the same answer, and that's correct. But let's not do that, or for the moment. For the moment, let's not do that. In order to understand what it would mean to have a time non-translation invariant system, some parameter of the system. It could be the electric field. Another parameter, we have a harmonic oscillator, a spring. X dot squared is the 1/2 mx dot squared is the kinetic energy, and the potential energy V is k over 2 x squared, where k is the spring constant. You can imagine situations where the spring constant might change with time. I'll give you an example. You put the spring, the whole spring and everything else, into an electric or a magnetic field, and you turn up the electric and magnetic field. The electric and magnetic field has a small effect on the atoms and the interatomic spacing and all sorts of things. The net effect could easily be a small time dependence in the spring constant. That would be another example that if you didn't worry about the external conditions and you only worried about the particle on the end of the spring, you would say that, that you did not have time translation invariance. We're going to find, after a little break, that time translation invariance implies energy conservation. On the other hand, you could say, well, what does that mean for when you don't have time translation invariance? What it means is there's an exchange back and forth between the thing you call the system and the rest of it of energy. Energy being transferred back and forth, in this case, between the capacitor and the particle, or whatever it was, whatever the agent was that was causing the change in the spring constant, transfer of energy. So from one point of view, you can think there was no symmetry, and the energy wasn't conserved. From a bigger point of view, where you take more into account, you would say there was a symmetry. If you translate the entire experiment back and forth in time, and in that case, the full energy, including the energy of the capacitor, plus the energy of the particle, plus whatever energy there is that causes them to interact, that will be conserved. So after about 5 minutes, we'll come back and we'll talk about energy conservation, which will bring us to the Hamiltonian, which is really where we want to go.
Just one quick one.
Mm-hmm. But did they say delta x equals epsilon?
Well, I mean, I just, well.
That's great. I love that. It's much better. Delta x equals epsilon. Because I hate delta x equals delta.
Yeah.
Yeah.
Like the formula up at the top right of the board there is,
Yeah.
unless you know what it is,
Yeah.
it's really confusing.
Yeah. Yeah, we could replace all these on this side by epsilon. Why didn't I think of that? Yeah.
It's a good book.
Which?
It's Hamiltonian's Magnificent Theorem or something like that.
Oh, I don't know about it.
It's everything that
It's a technical.
first-year physics student should know about Newton's theorem.
Okay. Who wrote it? You don't, maybe not. Well, put it online. Put it online. Put it on the website. Do you know how to put it on the class website? Emmy Noether's wonderful theorem, magnificent theorem. Yeah. Yeah.
Since we never here define the Lagrangian other than the difference between a kinetic energy term and a potential energy term, is it the case that in classical mechanics, it's always kinetic energy minus potential energy, but they don't always divide neatly between quadratic of speeds and function of...
If they don't divide up into quadratic in velocity and quadratic in, and a function of position, then there's no sense in which you can think of it as a potential. It's just a Lagrangian. It's just.
So how do we define it in general within a given...
It's a function of q's and q dots. You say, well, the question is not how you define it. The question is, where do you get it from? One answer is you might get it from experiment. Another answer is you might get it because you already know the equations of motion from somewhere, and so you look for a Lagrangian which gives that. Another possibility is you have some preconceived theoretical prejudices about the way the thing should look. But somewhere from some place, either experiment or just trial and error until you match the equations of motion, or a theoretical prejudice, you are handed a Lagrangian. The Lagrangian may be simple and have the form of a quadratic thing in velocities minus a function of the positions, or it may not. In any case, what do you do with it? What you do with it, incidentally, well, okay, we'll come to it. What do you do with it? You apply Euler-Lagrange equations to it, and that gives you the equations of motion. And you solve them. And that tells you how the system moves. All right, so we're going to take an abstract look at it now and assume there is a Lagrangian. Again, where it came from is not our business for the moment. Let's talk about what it means for the Lagrangian, or for the to have a time translation invariance. Let's take again this. Let's start with this very simple system. Let's say the harmonic oscillator, the Lagrangian for that system is just 1/2 m x dot squared. I'll use x now minus k over 2 x squared. K is the spring constant, the Hooke's law spring constant, and this is it. If k is constant, then we say the system has time translation invariance. If k varies with time, it doesn't. All right, so how do we generalize that idea? How do we generalize that idea? By looking at the Lagrangian, how do we know if it has time translation invariance? And it's very, very simple. If the Lagrangian is only a function of the q's and the q dots, but does not have an additional explicit dependence on time, then it's time translation invariant. If the parameters of the problem, for example, k or any other parameter, has a time dependence, then you add that into the dependence of the Lagrangian as an explicit dependence on time. I'll tell you what that means more clearly. The question is, if you know q and q dot, do you know the Lagrangian? Or do you also need to know the time? In the case of a particle moving in a varying electric or magnetic field, in order to know what the Lagrangian is at an instant of time, you need to know what time it is. On the other hand, if it's not varying with time, then there's no explicit time dependence here. So an explicit time dependence means a time dependence above and beyond the time dependence that's there because Q and Q dot are changing with time. An explicit time dependence which has to do usually with the fact that the system, that you've treated only a part of the system, and there are parameters in your description which are time dependent because something else is going on. All kinds of examples. Here's an example. You have a heavy dumbbell. The heavy dumbbell is so heavy that, nothing reacts. It doesn't respond to the motion of a little ping pong ball over here. If the dumbbell is standing still, and furthermore, we'll assume that the dumbbell exerts a potential energy on the particle. Could be gravitational, for example. The gravitational potential energy of each of these heavy weights here would create a potential energy and therefore a force on the particle. Now imagine that the dumbbell was turning. It was spinning or revolving around a pivot at the center here. We're not going to try to solve the equations of the dumbbell. We're just going to say, look, we know this dumbbell is so heavy, we know how it's moving, and we simply put that in as input. Then the forces on the particle here will be time dependent. The Lagrangian will be time dependent because the potential energy will be time dependent. That would be an explicit time dependence here. What does it mean to say you have time translation invariance? Very, very simple. It simply means that there is no explicit time dependence. That's it. You know everything about the system if you know the Q's and Q dots at an instant of time. You don't also have to say what time it is in order to know what the value of the Lagrangian is. That's all it means. No explicit time dependence in the Lagrangian. I'm going to work out the conservation of energy for you, assuming that there is no explicit time dependence. And then I'm going to tell you, it's in the notes, it's worked out in the notes a little more generally, with an explicit time dependence. I want to do it the simplest possible way so that you don't get lost in details. And then I'll come back and tell you what happens if you do have an explicit time dependence there. So let's suppose that you thought that the Lagrangian was the energy. You didn't know that the Lagrangian is T minus V and that the energy is T plus V, and you just thought, oh, maybe this thing called the Lagrangian is the energy. I can check that by seeing whether it's conserved. You know, if it's an ordinary system and we expect there to be a conservation of energy, let's just try it. Let's just try it and see if it's conserved. How do you find out? Well, first of all, you start by saying the Lagrangian is some function of all of the Q's and the Q dots. Let's calculate its time derivative. What better way is there to calculate whether it's conserved than to calculate the time derivative? Okay, so let's try to calculate this. d by dt of the Lagrangian. Now, let me explain what this means. The system moves through the coordinate space, and as it moves through the coordinate space, the potential and kinetic energies change with time. The question is, as you move along a trajectory, is the value of the Lagrangian changing or not? All right, so how do you calculate this? You just say, well, first of all, this is equal to the derivative of Lagrangian with respect to the coordinates times the time derivative of the coordinate plus, this is the change in the Lagrangian when you change the coordinate times the change per unit time in the coordinate, plus partial of L with respect to Q dot, Q double dot, right? Q double dot. You differentiate with respect to the argument, and then you multiply it by the time derivative of the argument of the function. Is that clear? All right, this is basic calculus. I can't motivate this except to say it's the change in the Lagrangian when you change a coordinate times how fast the coordinate is changing, plus the change in the Lagrangian because the velocity may be changing with time, times the time derivative of the velocity, which is the second derivative. Okay, now let's assume that the motion along here satisfies the equations of motion. Okay. First of all, what is dl by am I missing something in this formula? A summation, right? The time derivative, each one of the coordinates can enter into it, summation over I. Each one of the coordinates is changing. The Lagrangian depends on each one of the coordinates, and so there's a sum over I in this formula here. Okay, let's manipulate it. Now we do a little bit of magic, and the magic is always the same. There's not much variety in this business. Once you learn the trick, it's pretty much a one-trick game. Okay. Well, let's start with this one. dl by dq sub I dot. What is that? It's p sub I. That's the definition of p sub I. Remember? dl. Oh, I have this habit of sometimes switching between script and, okay. dl by dq sub I dot is definition p sub I. That's the definition of the canonical momentum conjugate to q sub I. So let's use it. I mean, this is just definition and not doing anything very substantial here. P sub I times q sub I double dot, which is, incidentally, q sub I dot dot. Q sub I double dot is also q sub I dot dot. It is. Well, I suspect we're going to use that q sub I double dot is q sub I dot dot. Okay, now, this is plus q sub I dot, but what's dl by dq sub I? P dot. That's Lagrange's equations. dl by dq sub I, that's p sub I dot. Okay? So we get p sub I dot here, sum over I. Now look at what we have. We have the time derivative of this. Well, I'll write the formula and I'll show you where it comes from. This is the same thing as d by dt of p sub I q sub I dot under the summation. Can I take away the summations? Let's take away the summations, just to unclutter the formula. In fact, I mean, this is true even without the summations. This is what we have. P sub I, why is this true? Well, the time derivative of this product is the time derivative of the first factor times the second factor. That's this one, time derivative of the first factor times the second factor, plus the first factor times the time derivative of the second factor. Here is where we make use of the fact that q double dot is q dot dot. If you know what I mean. And if you don't worry about it. It just means... Which one?
All the way to the right.
Yeah. One dot. Right, just look at it. d by dt of this whole thing, this is all here, all inside a bracket. The derivative of a product is the sum of two terms. One term would be p dot q dot, that's this, and the other term would be p times q double dot. Okay? That's a little magic. And
On the right-hand edge, where, is that two dots or?
no, that's one dot. One dot. I see. Okay. Sorry about that. One dot. Now does that make you happier? Good. Right. P dot q dot plus p q dot dot. So this is an equality. All right. Let's go back and put back the sum. I won't actually put back the sum because I don't want to clutter it up, but think about the sum. What have we found? We found that the L by dt happens to equal the time derivative of something else. Happens to equal the time derivative of p sub I, q sub I, dot sum over I. Well, that's interesting. You have one time derivative equaling another time derivative. First of all, the Lagrangian is not itself conserved. The time derivative, it is not conserved. It has a right-hand side, and in general, this right-hand side will not be 0. But supposing we now subtract these two and set that equal to 0, now, in fact, we have that the time derivative of some quantity is equal to 0. All right, so let's write down what that quantity is. Let's look at it. It's the Lagrangian minus the sum over all the canonical coordinates, all the coordinates, sum over I, p sub I, q sub I dot. That is conserved. It's got a name. I'm going to write down its name over here. It's called minus the Hamiltonian h. You'll see in a moment why that minus is there. You could call it h if you wanted to. That would be fine. You could call it h. It would still be conserved. It's a historical fact. It's just a historical fact that it was called minus h. So we write then that h, which is a conserved quantity, is the sum over all the directions in the coordinate space, p sub I, q sub I dot, minus the Lagrangian. Okay, let's work this out and see what it is for some simple examples. Let's take some simple examples. Simplest example, L equals 1/2 the mass times x dot squared minus v of x. What is this? This is a particle moving in a potential energy v of x. Let's work out what it is. Of course, here I've substituted x for q. Whenever I'm thinking about a particle on a line, I'll call it x, but it's really just q. Okay, first of all, what is p? P sub I, or just p, there's only one coordinate. P is mx dot, right? So let's calculate what h is. H is, first of all, there's no sum now. There's only one coordinate. It is p, which is mx dot. And what's q dot? Just x dot. For some odd reason in my notes, this is written as this times x dot. I think I just wanted to emphasize that it was a product of two things. Just, I'm going to go and erase that and just call this x dot squared. So pq dot is nothing but mx dot squared. You might have noticed that it's not a half mx dot squared. Now let's subtract the Lagrangian. Subtracting Lagrangian is minus, in brackets, m over 2 x dot squared minus v of x. Okay, what do we get all together? We get 1/2 mx dot squared from this and this. Mx dot squared minus 1/2 mx dot squared. That's just mx dot, that's just m over 2 x dot squared, kinetic energy. And what happens to the v of x term? Magic. V of x minus v of x in the Lagrangian gets converted to plus v of x in the Hamiltonian. You see what happened? Minus times minus is plus. This is the conserved quantity, not the Lagrangian itself. Lagrangian is not conserved. You have to add that term in, or subtract it off, or whatever. And that changes the sign. See, the Lagrangian has minus v of x, and so minus the Lagrangian has plus v of x. That's as simple as that. This, of course, is what we usually call the energy. This is very general. We could have done it for any number of particles. It would have come out exactly the same way. Each particle would have made its contribution. Any number of dimensions of space, any number of particles, exactly the same thing would have happened. So we find out, yes, there's a conservation law. And that conservation law, at least in the cases where we recognize what energy is, potential plus kinetic, it's just the energy. More generally, when the Lagrangian doesn't divide up in a recognizable and simple potential and kinetic energy, nevertheless, this quantity is conserved. We proved that without assuming that the Lagrangian had any particular special form. Starting at the top, no special form for the Lagrangian. We did use a definition that the L by dq dot is equal to P, but then the rest of it, right up to here, did not in any way depend on the specific form of the Lagrangian. So whatever the Lagrangian is, PQ dot minus the Lagrangian is a conserved quantity.
As long as there's no time dependence.
Yeah, we'll come back in a minute. Right, as long as there's no time dependence. Okay, in the notes, I worked it out with the time dependence, but you can kind of see what would happen. If there's an explicit, let's see, supposing the Lagrangian explicitly depended on time. Yeah, let's just go back. Oh boy, I wish I were 2 feet taller. I really don't want to push this up and pull that one down. Okay, we'll do it. For you, anything. Am I missing something here if there was an explicit time dependence? Partial of L with respect to t. In other words, you keep the q's and the q dots fixed and just differentiate what that corresponds to. In our case over here where the spring constant might have an explicit time dependence, is just to differentiate the time dependence. You would have a k dot times x squared, 1/2 k dot times x squared. You'd be differentiating this thing over here. So yeah, there's another term there. Let's see if we can track the other term. Where did it go? One more term, that's the L. Okay, so the L by dt then would have, on the right-hand side here, partial of L with respect to t. Now, first of all, what is the difference between dl dt, this, and this? This, the left-hand side here, this dl dt is actually the true derivative with respect to time along the trajectory as the particle moves or as the system moves. In other words, it contains not only the partial derivative with respect to t, but also the fact that the q's are changing. That's this side over here, or this one over here. This is what you get just by doing nothing but differentiating the parameters in the Lagrangian. So this is what we get, and this is equal to minus dh dt. Let's see, this thing over here, L minus PQ dot That's minus h, so this is equal to minus dh dt. So we have the theorem then that the time derivative of the Hamiltonian, if there's an explicit time dependence, is equal to minus the partial derivative of the Lagrangian with respect to time. In other words, energy would not be conserved if the Lagrangian had a explicit time dependence. Here, from this case over here, what is the dl by dt? The partial derivative. Partial derivative of L with respect to t. No explicit time dependence here, only here, is minus k dot of t divided by 2 x squared. What this says is wherever the particle happens to be, at whatever x it happens to be at, happens to be over here, then if you want to know, sorry, this is dl by dt, and that is equal to minus dh by dt. I just use this over here. Okay? So the energy in this case is not conserved. Its time derivative is not 0. It's x squared, whatever x squared is, times the time derivative of the spring constant. The time derivative of the spring constant translates into a time derivative of the energy of the oscillator. Now, of course, if x happens to be 0 when you're sitting at the origin, then this is 0. But if any other situation, wherever x happens to be, there will be a time derivative of the energy. Okay? And as I said, that is because you've separated the system into the thing that you're looking at and ignored the thing which is causing the change of the parameters. All right, that's the notion of a Hamiltonian. Let's see.
Question?
Yeah.
You said that energy is not conserved. Does that mean the definition of energy is the derivative of the Hamiltonian? Is that the definition of energy?
The definition of energy is the Hamiltonian period.
I'm sorry, yeah.
Yeah.
Okay.
Mhm.
Definition of
Yeah. Yeah. As I said, in all the cases where the Hamiltonian can be written in a familiar form of a potential, kinetic minus a potential, then the answer is the kinetic plus the potential. When it's written in an unfamiliar form, the Hamiltonian tells you what the rule is for the definition of energy. And if you treat the whole system, including the dumbbell, the rotating dumbbell up there, you treat it all together, energy will be conserved. Yeah.
Explain this again in the context of the example that you had in one of your earlier classes.
Which example?
Of a stationary particle and an observer on a merry-go-round. Where, all of a sudden we've got the centripetal force and the Coriolis force and all of that. Whereas, because of the rotational invariance.
Well, because what?
Because of the rotational invariance, the Lagrangian didn't change.
Remember that in that case, we were not just talking about a rotation, we were talking about a time-dependent rotation. We weren't just talking about a coordinate change or a time translation. We were talking about a rotating coordinates that sit there and rotate. That's a different story. In the first examples we talked about tonight, we just do some change of variables, and it's that change of variables. It doesn't change with time. It's just a fixed change of variables. In the second example, it's a time shift. The rotating coordinates is a separate beast of its own. We could take the Lagrangian that we computed, including the effect of the rotation, just take that as an abstract Lagrangian and ask what the Hamiltonian is associated with it. I was going to wait to do that until we talked about particles in electric and magnetic fields, because they're very, very closely related. I think I will wait on that. Now, I don't know whether it's a good idea to continue now with more material or whether you're all saturated. We've been going for an hour and a half. What does that mean?
I just want to ask a question.
Okay.
So just to kind of summarize so to get it clear, we
Yeah.
defined Lagrangian, and we've discovered that it's a derivative of it. Let's see, derivative.
No, Lagrangian wasn't the derivative of anything. We calculated the time derivative of the Lagrangian.
And then we took the Lagrangian of it, and then we can come up with
Yeah.
Hamiltonian.
So let's summarize everything we know up till now about Lagrangians. First of all, Lagrangians are functions of Q dot, and I'm simplifying, I'll leave out the little sub i's, and possibly also explicitly dependent on T. May or may not this explicitly depend on T. Okay. Lagrange's equations of motion, or the Euler-Lagrange equations of motion. Well, first, before we do that, P sub I is just, I keep doing this, dl, forget the I, by dq dot. Of course, there's a separate one of these for each I, but let's simplify. P is dl by dq dot. The Lagrange equations of motion are that P dot for each I is equal to partial of L with respect to the corresponding Q. Sometimes it's written as d by dt of partial of L with respect to Q dot on the left-hand side. But if I use the fact that dl by dq dot is called P, it's just P dot equals dl by dq. Okay, so those are the basic Lagrangian equations of motion. Then, next, so let's get everything here. If there is a symmetry, an ordinary symmetry, not a time translation symmetry, if there is a symmetry of the form delta Q, let's put an I in here now, F sub I of Q, shall we call it epsilon now instead of delta? Yeah, there were too many deltas in the formula, but the epsilon is just what we called before delta. If we have a symmetry of this type, if we have a symmetry of this type, then it follows that there's a conserved quantity, Q, Q, which is equal to the sum of all I of P sub I times F sub I of Q. And of course, Q dot is equal to 0. That's what it means to say that it's conserved. We proved that last week. Okay, we proved that last week. I quoted it this week, but we proved it last week. Okay. If we have time translation invariance, no, let's not write that. Let's do it without time translation invariance. All right. Generally, the time derivative of the Lagrangian along the trajectory of the system, the time derivative along the trajectory of the system, what do we find? That it was equal to minus or plus? d by dt, plus, right? Yeah, I think I have it right. Plus the explicit time dependence. Or if we transpose to the other side of the equation, we get this. Right? And then this just reads that minus dH dt is equal to plus dL by dt, where H is equal to the sum of the PQ dots minus the Lagrangian. Now, usually what you do in thinking about this, the way we thought about it up till now, the P's were definite functions of Q and Q dot. You get them by differentiating the Lagrangian with respect to Q dot. So this side here is something that's known in terms of Q and Q dot, and this whole thing here is written in terms of Q and Q dot. What does it give? It gives kinetic plus potential when there is a kinetic plus potential. So this is conserved. d by dt of H is equal to 0 when the Lagrangian doesn't have an explicit dependence on time. All right, this is basically all the equations that we've done up till now. Definition, Euler-Lagrange equation. If there's a symmetry, there's a conserved quantity, Noether's theorem. An ordinary symmetry, and if there's time translation, well, even without time translation, dH by dt is equal to minus dL by dt. Why did I write this way? Let's write it the other way, minus dL by dt. Again, the sign gets flipped here. That's funny. The sign gets flipped, but it's correct. Okay. So those are the equations. Go through them. Try to derive them. There's a small number of tricks in deriving them. Get familiar with them, and you'll find this is very easy. So the Hamiltonian, yeah.
If you take the simple case where T and V are discrete and separable, then Lagrangian is T minus V and Hamiltonian is T plus V, correct? Mm-hmm. And it seems that you can describe mechanics either using Lagrangian or the Hamiltonian.
Well, we have not discussed yet the Hamiltonian formulation of mechanics. We will.
Right, that's unknown.
Right, at the moment we have not.
The question is, it's the mechanic, the motion is some function of the Hamiltonian or the Lagrangian. Is there some reason to pick one over the other? Is that equivalent?
They have a different character to them, the equations. Is there some reason to pick one over the other? No, they're equivalent to each other. But they emphasize different features. The Lagrangian emphasizes the least action, or the stationary action idea. It really is the stationary action idea. That's where it came from. And it came from the idea of saying mechanics can be formulated in terms of an action principle. The Hamiltonian principle is different. It's more abstract. It's easier in many ways. The equations are very easy, but it's more abstract. And you might ask yourself historically, why the hell did Hamiltonian invent it in the first place? Well, he was playing around and just trying to sort out all the possible different formulations you could have. But of course, the Hamiltonian formulation played the central role in quantum mechanics, very central role in quantum mechanics. So I can't do that now. But we can work out the Hamiltonian theory. The point is, the Hamiltonian is not just the energy. It is the energy, but it's not its only significance. The formulation, the Hamiltonian formulation of mechanics, is a very different emphasis in a way than the Lagrangian. Well, we have a few minutes, so we can do a very simple example.
Another question, did Newton know about the, what we would call the Hamiltonian conservation of energy?
No, I don't think so. No. No. If he did, he didn't say.
But you know about kinetic energy? You must have if you did all the orbits.
so. No, F equals ma.
Okay.
Yeah, so no.
How do we know that there's always, that every system has a Lagrangian that corresponds to that? Is that just an experimental fact?
It is an experimental fact. It's also a thing that follows from the rules of quantum mechanics. So,
Is it theoretically possible that we could have a system that didn't have a Lagrangian?
I could write down equations of motion that didn't have a Lagrangian. But, you know, that's a counterfactual. If we didn't have quantum mechanics, what would be true? Well, I don't know what would be true if we didn't have quantum mechanics. We have quantum mechanics. So, classical mechanics does not precede quantum mechanics logically. Quantum mechanics precedes classical mechanics logically. So if you want to know why something is true in classical mechanics, or why, well, yes, if you want to know why classical mechanics takes on a certain form, there are two possible reasons. One of them could be that the things that you're happening to talk about are required by logical consistency of the equations. You know, this equation, dq by dt is equal to minus dq by dt. I think we know we don't want to write that equation, right? We just don't want to write that equation. That equation, well, it does say dq dt is equal to 0, equals 1. That's a bad equation, okay? So we don't write it down because it's mathematically inconsistent. Right? But we could write down an equation which is consistent. dq by dt, and now I mean dx by dt, I might as well write dx by dt, is equal to some known function of x, is equal to x, or minus x. That's a perfectly good equation. You can solve it. It has, you know what the solution is. The solution is x is equal to e to the minus t. It's perfectly good. Nothing wrong with it. Why can't it be a fundamental equation? It can't be because quantum mechanics doesn't have systems that behave that way. And that we do understand why. But I can't tell you now. This question keeps coming up over and over and over again. Please accept my, be patient, be patient. I cannot tell you why classical mechanics has the form that it has, except to say that if it didn't, quantum mechanics would not make sense. Yeah.
For every real system, there's a Lagrangian, but for every Lagrangian, there's not a...
That's almost certainly true. Right. Not everything you write down is realized in nature as a real system.
Lagrangian is basically just a tool for inventing potentials.
Well, it's not a tool for inventing potentials. You could invent potentials without the Lagrangian, but it's a tool for inventing mechanical systems, if you like. You know, it also is a powerful tool for solving certain problems, which I haven't emphasized. Maybe I should at some point emphasize or give you an example of a system which is easily studied with the Lagrangian method, which is awfully hard to think about by F equals ma. That makes it easy, but I was thinking about the double pendulum. Yeah, the double pendulum, a pendulum hung from a ceiling with another pendulum hung from it like that, swinging, the whole thing swinging. Awfully hard to think about the forces and to think about the way you do it is you write down, you first invent some coordinates. The coordinates could be this angle, and let's say, I don't know, maybe the angle relative to the vertical over here, phi. We fix the length of the pendulum. And then we write the velocity of this particle and write 1/2 mv squared. We write the velocity of this particle, also write 1/2 mv squared for it, or the v's being determined in terms of theta and phi, and then add the potential energy. And then you have a Lagrangian. It's rather easy to do in this form. And once you have the Lagrangian, you grind out the equations of motion by the standard method. Much, much easier. then trying to think about the forces acting. And so the Lagrangian is often a compact way to solve a problem. You figure out what the potential energy is, you figure out what the kinetic energy is, you subtract them from each other, and you got the Lagrangian. Once you have the Lagrangian, you apply these rules.
Like three particles, except that you've said that one particle is so big and dominant that it's an anchor.
Yeah.
So
what's the point?
It would be like sun, planet, and moon. You know, sun, earth, moon.
Mm-hmm. Mm-hmm.
Same kind of.
Mm-hmm. Yeah. Right. But I think this is a nice problem to set up and solve using Lagrangian, which will show you the power of it and how easy it is to solve problems. Writing the Lagrangian first and then working out the equations of motion. It's also extremely useful if you're changing variables. Instead of trying to change variables in each of the equations of motion, you change the variables in the Lagrangian. This is what I showed you time before. How you go to the rotating coordinates. It's easier to just compute the Lagrangian than it is to take the equations of motion and transform them. That's almost always harder. Yeah.
To solve that problem, you say the Lagrangian is equal to T minus V.
Yeah.
And I think earlier today you said you can't always say that.
All right, but in this case it is because it's really just a collection of particles.
I don't understand. How do you know when it's not T minus V?
Things which are made up out of ordinary particles, it's always T minus V.
It's T minus V in an inertial frame.
Yeah, so it's T minus V in an inertial frame. But we're in an inertial frame. We're watching this from an inertial frame.
That's as long as they're non-relativistic.
It's right. It's non-relativistic. There are no magnetic fields present. Then it's just T minus V.
Collisions which change momentum or extreme momentum.
Yes. Collisions are due to forces. Forces are due to potential energies. Collision. Why does a collision happen? A collision happens because there's a repulsive force between particles. You seem puzzled by that. You seem surprised. Oh, inelastic collisions. I guess is what I mean. Well, inelastic collisions involve many, many particles. I mean, it's still true that inelastic collisions are just collisions between lots and lots of particles. But the particles can get excited into motions that don't correspond just to the net center of mass motions of these particles. In addition, they can heat up. But in the end of the day, the equations for each particle is just Lagrange's equations.
Physicist, if the particle is a baseball and it's hit by a bat, then I can analyze that in terms of F equals ma.
Not if you want to keep track of the heat that's generated in the baseball when it gets whacked. Actually, it'd be very hard to right. You might smash the baseball, the bat might get broken. Not so easy.
How about a rigid body, a finite extent?
Yeah.
That
you can often study with F equals ma. Yeah.
The Lagrangian and so on is a good way to...
T minus V.
Huh?
T minus V. Yeah. Yeah, we could talk about rigid bodies and Lagrangians for rigid bodies, and maybe that's a good exercise. Yeah.
So you're talking about conserved quantities and classical versus quantum mechanics. Does the energy time uncertainty relation imply that energy is not strictly conserved?
No. No. It says, what it says is that to measure it accurately, you have to take a long time. That's what it says. Right. Strictly conserved, but if you want to know it accurately, it takes a long time to measure it.
I think what I hear you saying is that Lagrangian can't approach the Hamiltonian approach and the traditional, Newtonian approach. Those are all sort of logically equivalent. So does that mean that you could derive technical?
Well, they're logically equivalent under the circumstances that they apply. Now, you can invent Lagrangians which don't naturally lend themselves to equations mx double dot equals f of x. Here's a Lagrangian. Okay, let's work out a non-standard Lagrangian, but it's a perfectly good Lagrangian. From the Lagrangian point of view, there's nothing wrong with it. Instead of writing q dot squared, well, minus some v of q, let's make it definite. Minus q squared over 2. I've left out the mass and the spring constant. That doesn't matter. Let's change it. Let's put another q squared here, multiplying the q dot squared. It's perfectly good. It is of the form of an L of q and q dot. But it doesn't have, we could add something else here. We could add q dot, for example. It just doesn't lend itself to a description in terms of a conventional kinetic and potential energy, particularly with this term here. But still, we could write out the equations of motion. Let's do it. Okay. So partial of L with respect to q dot, that's p. What is p? P is not equal to q dot. It's equal to q squared q dot. Where'd that come from? Derivative of Lagrangian with respect to q dot now contains a q squared. Okay. So our equations of motion are p dot equals partial of L with respect to q. Let's see what we get. P dot is q squared q double dot, that's from differentiating this, plus 2q q dot squared. Where did that come from? Differentiating this with respect to time gives us 2q times q dot, but now we have another q dot there. And what's that equal to? That's equal to the derivative of Lagrangian with respect to q. Now q occurs in both of these. Q occurs in both of these. So what's the derivative of Lagrangian with respect to q? It's q times q dot squared minus 1, I believe. Is that right? Yeah. Both of them have q squared over 2. So when I differentiate with respect to q, it just leaves a q, and then it multiplies q dot squared minus q. So what does this give? It looks like it gives q squared q double dot plus q dot squared equals minus q. Okay, there's nothing special about this. It's just an example. I can't hear you. I could. Unless q is 0. Yeah, we could divide by q everywhere. Okay, we could calculate the Hamiltonian if we wanted to. We could calculate what the energy is. Let's calculate what the energy is. We just calculated what P is. P is equal to q squared q dot. We're supposed to multiply P by q dot. So let's do that first. PQ dot, that's q squared q dot squared, minus the Lagrangian, minus q squared q dot squared over 2 plus q squared over 2. So in fact, it does have, it looks like q squared q dot squared over 2 plus q squared over 2. It does look like t plus v. We could think of this as t, and this is v. We can make up examples which are more complicated where it won't naturally break up in that way.
Squared T?
Say it again.
Is Q squared, Q dot squared really T? Is that connected?
Yeah. Well, yeah, if you call this T, yes. If you call that T. Yeah. Notice all that happened when you went from the Lagrangian to the Hamiltonian, again, was the same thing. The Q squared changed sign, and the other term stayed the same. Right. Yeah.
How do you account for friction in the Lagrangian?
You don't. You don't. Friction is due to the collective, to the motion of tiny particles which are too small to see. You can think of them as being all a large number of particles that you can't keep track of, but they're described by the same kind of description, but you can't keep track of them. That's all. The Lagrangian equations don't describe friction.
Would you define a potential
Not a big sort of lacking. It's a major thing in the world.
What's that?
Friction is a major thing in the world. Seems like
There's no such thing as friction at the level of elementary particles. There is no such thing as friction at the level of electrons and protons and neutrons. Friction is a statistical effect of lots and lots of particles that you just can't see.
Do you know how Hamilton arrived at his formulation? Was he playing with energy and said, oh, it has this form?
I really don't know. I wasn't there.
No, I don't know. Right.
You said that Lagrangian is not always T minus V. Is there some more general expression for Lagrangian? How do you get these Lagrangians that aren't T minus V?
Experiment, guess, or some symmetry principle.
But conceptually, though, is it the case that, would it be correct to say that to build a Lagrangian function, you're going to have energy terms that correspond to kinetic energy, and then you're going to subtract the sum of everything else that contributes to energy?
What?
Are you going to have, if you're going to construct a Lagrangian function, right? It seems like you're adding up a bunch of energy terms. So you have to have some concept of what might constitute a good candidate.
I know. But, you know, if we were studying calculus, and I said, here are the rules for doing a derivative, you do the following things, f of x plus epsilon minus f of x divided by epsilon. Would you raise your hand and say, where do you get the function from? This is a calculus. This is a calculus of, it's a systematic calculus that underlies classical mechanics. The fact that real systems conform to this, experiment, guess, or symmetry, but basically it's an abstract mathematical system. It's an abstract mathematical system, and if you ask where do you get the pieces from, these places. How is it that, one more, I'll say it once more. How is it that real nature, classical nature, conforms to this abstract system? Quantum mechanics. So there's nothing more to say. There's nothing more to say except to study this mathematical system and understand how it works. There is a little bit more. We haven't gotten yet to the issues of reversibility and how and whether this is related to the things that we talked about in the very first lecture. Remember what we talked about in the very first lecture? Laws of physics which were both reversible and deterministic. And we meant something by that. We meant that you don't lose information, that trajectories don't run into each other. In fact, that this whole story is closely related to that. We will get to it. We will get to it, but in steps.
So I was just going to say that going back to the Lagrangian for classical mechanics, really the way we got it was we went to variational calculus.
We went to what? Yeah.
Variational calculus.
Well, we started with
general.
we started with the principle of least action, or Newton's stationary action.
But I mean, even there, the way you came up with the function that you put in that integral is this working back from the answer. You wanted one that would give you the equations of motion, right?
Well, yes, in that particular case, yes.
So even for quantum mechanics, is that the same way you get the Lagrangian? You have, I don't know, the Schrödinger.
Quantum mechanics logically begins with the Hamiltonian, and then you work your way through to the Lagrangian. And in quantum mechanics, the Hamiltonian is a much, much, much more intuitive concept, believe it or not. The Hamiltonian in classical mechanics is an abstraction. It's a deeply abstract thing, and the Hamiltonian formulation of mechanics. Whereas in quantum mechanics, it really is very intuitive. But we can't start with quantum mechanics because it's too alien. We need some concepts from classical mechanics to start with. One of these days, maybe I'll try teaching it the other way. We'll start with quantum mechanics. Yeah, we could do it. We could do it, and then derive classical mechanics as a limit.
Can you describe friction in terms of quantum mechanics?
You cannot describe a particle moving, for example, through a viscous fluid by quantum mechanics without describing all the particles of the viscous fluid. If you want to study a quantum mechanical version of an object moving through a viscous fluid, it is necessary to keep track of all the particles. String theory, same thing. Friction is simply just a very, very complicated effect of lots of particles. Statistical.
For more, please visit us at stanford.edu.